Today we're going to be looking at inverse functions, and more specifically we're going to be talking about the concept of a one-to-one function. So we're going to determine if a function is one-to-one. Now, what is this inverse function that I talked about? Now, if you were thinking of a function as like a process, like we did in the previous section, what if we look at functions that have this reverse process? So I guess a real life process that has a reverse process would be like putting on socks and then putting on shoes, because the reverse process would be taking off shoes and then taking off the socks. And so we know that that type of process is reversible. Now, that there are going to be some that are not, like cooking a roast. How do you uncook the roast? You can't. And so because you can't uncook the roast, that is not a reversible process. Now, relating that to functions, to have this idea of a reversible function, for us to create this function that I have right here of 2x plus 1, if I started with x, well, the first thing that I could do is multiply by 2, and that's how I get 2x. And then if I add 1, I get my 2x plus 1. And so this reverse process would be, if I start with the 2x plus 1, well, if I subtract 1, then I get 2x. If I divide by 2, I get x. And so this reverse process seeks to undo those steps that we just did. Okay, it seeks to undo those steps that we just did. Now, if you noticed that reverse procedure, okay, when we undid it, so going back and looking at it, it left us with x. Now, if we examine both of these functions, here's the original, right? I started with x, I multiplied it by 2, I added with 1. The reverse procedure was I took it, subtracted by 1, and then I divided by 2. This would be that reverse function that I talked about. So now let's examine what happens if you actually take the composition of both of these functions. And so what if I wanted to find f of g of x? So this is saying take my g function and plug it into my f function. So if I do that, I get 2. Now my g function is x minus 1 over 2. And then I have that plus 1. Well, if I reduce it, the 2's cancel out, so I get x minus 1 plus 1. Those cancel out, and I'm left with x. If I do my f function and plug it into my g, that's going to give me 2x plus 1, right? I plugged that in for x here, minus 1 all over 2. Well, the 1's cancel out, so I get 2x over 2, and the 2's cancel out, and so I'm left with x. So it's kind of like that observation that we just did. When you take the reverse and the original and you create a composition of them, it doesn't matter which order that we did, notice that we were left with this x. So let's define some things. Now, the main idea of what just happened is that the outputs, they turned into its respective inputs. That's why they kind of switched. They undid each other. Now, as we talk about this concept a little bit further, we're going to kind of define a few extra things. But going into that, if I have those two functions, I can deformally find, say, that this f and g are two functions such that if I take the composition of them in either or equals x for all x in the domain of f, and if I take that for x in all the domain of g. So taking this composition of each other, if they simplify into this x, then I can say that f and g are inverses of each other, and that the functions f and g are said to be invertible. So one of the ways for us to be able to define or say, hey, I have these two functions, are they inverses of each other? Is one of them this quote-unquote reversible function? I can take the composition of them, and if they simplify into x, I know that they're going to be inverses. So once I've established that my two functions are inverses, one of the properties is that the range of my f function is the domain of my g function. My range and domain switched. And the domain of my f function is the range of my g. My domain and ranges switch. So for an inverse function, you're swapping my x's and y's. Now, another way of looking at it, f of a equals b if and only if g of b equals a. I'm swapping my input with my output, swapping my input with my output. And A and B is on the graph, so this is graphically, of f if and only if B of A is on the graph of G, meaning my input and output, my x and y, switched with my y and x. So if we know that it's an inverse, then I can make the conclusion that for each of my functions, to get to the next function, I'm going to swap my x and y's. Now visually, this is an example of that. If I took my f function, which is 3x plus 4, and my g function, which is x minus 4 over 3, and if I were to graph it, to take the inverse functions, all I did was I swapped the x and y's. Now when you do that, you get this reflection about the equation y equals x. And so looking at this function here, if you notice, there's the y equals x, there's like this reflection that's happening over it. Now I said we're swapping the x's and y's. Well, notice if this looks about like 1, negative 1, well, if I swap the x and y's, that becomes negative 1, positive 1. If I were to say that this looks like 2 and almost a half, well then almost a half, and then it's about 2. So my x and y's are swapping each other. Okay, my x and y's are swapping each other. Now, a few unique properties of our inverse function is there is exactly one inverse function for f. So if I have my function, there's no other inverse function except a single inverse function. And the way that we denote it is f inverse. Now, this is not f to the negative 1 power in the sense of, oh, I need to flip it. Okay, it doesn't mean you have to do the reciprocal. This is notation. This is not an exponent. This is notation. So it's a way for me to say, well, if I have a bunch of functions, let's say I have my f function, instead of writing g of x, which it makes us, and it kind of forces us to think, wow, that g has nothing to do with the f. If I know that my g of x is an inverse of f, I can write that as f inverse of x. If I know that this is the inverse to this, then I know I can write it as f inverse. And so those would be inverses of each other. And then also, the graph of y equals f to the negative 1 x is a reflection about the graph or the line y equals x. So just know that if I graphed both of these, there's going to be that reflection across that y, and we visually took a look at that in this example here. Okay, there's the line y equals x, and there's like that reflection that's created across that line. Now there's a few ways to know if a function has an inverse. Now one of those ways we kind of already talked about, right? What if I take the function and I already know a function, and how do I know if they're inverses of each other, right? We take the composition of them. But what if I just have a function f of x and I want to know, well, does that function actually have an inverse? And what I mean by that specifically is that the inverse is also a function. Okay, so that's kind of important. Most functions that we have, we can manipulate it to where it has a quote-unquote inverse, but it doesn't mean that that quote-unquote inverse is also a function. So to determine if a function has an inverse, meaning that the inverse is also a function, okay, so make sure we clarify that, we have to determine if the function is 1-to-1. And so that's going to be really, really important. Now that what all that 1-to-1 means is for every 1x, there's only 1 y, and I could switch it the other way. For only 1 y, there's only 1 x. So it means my x's and my y's will never repeat each other. Now there's two ways for us to be able to determine that. The first is by this definition. It says a function f is said to be 1-to-1 if f matches different inputs to different outputs, which means this statement here. F of c equals f of d, then I can assume that c equals d. So we would use this and we would prove it. So this is going to be like a proof. So my function is 1-to-1 if and only if whenever f of c equals f of d, and then I show that c equals d. So you start with this and then you show this. The second is graphically. and that's going to be the horizontal line test. And so a function f is 1 to 1 if and only if no horizontal line intersects the graph of f more than once. So let's kind of take a look at a few of these. So the first, let's show that the function is 1 to 1 analytically. So we're going to use this definition here, f of c equals f of d, then c equals d. So let's hypothetically assume, let's say, what if my function is 3x plus 4? So I need to show f of c, so we assume with f of c equals f of d. So trying to show that, my f of c, so my f function with c plugged in, I get 3c plus 4 equals, now my f function with d plugged in, 3d plus 4. Now I need to algebraically simplify this to show that c equals d. So I could subtract 4 on both sides, so I get 3c equals 3d. Then if I divide both sides by 3, I get c equals d. So because I was able to show that c equaled d, I can make the assumption, therefore, my function is 1 to 1. So like I said, you assume f of c equals f of d, and then so there's my f function with c plugged in, there's my f function with d plugged in, and you ... simplify it down to where you get c equals d. Now if you can't show this, then your function is not 1 to 1. Now visually, if I wanted to use the horizontal line test, we said that a function is 1 to 1 if and only if no horizontal line intersects with the graph more than once. So if I draw in these horizontal lines, only intersects once, once. So I could say that this function is 1 to 1. But on this one, if I draw in that horizontal line, well, it intersects twice there. I know we were thinking, oh, look at that. It only intersects once. That therefore it's 1 to 1. Haha, I proved you wrong, Mr. Duvall. Doesn't work that way. If at any interval or at any value that I draw on a horizontal line, if it intersects more than once, then it's not going to be 1 to 1. And so it may have a quote-unquote inverse, but the inverse is not a function. And so I cannot write it in that fashion. I'm not allowed to use that notation. So let's look at a few examples here. So it says determine if the following functions are 1 to 1 in two ways, analytically and graphically. So we said analytically, if we want to determine if our function is 1 to 1, we said f of c equals f of d. Simplify that down, do I have c equals d? So we start with that. So f of c equals f of d. So 1 minus 2c over 5 equals 1 minus 2d over 5. So now I need to try and get it by itself to where it's c equals d. So I can multiply both sides by 5. So if I do that, I get 1 minus 2c equals 1 minus 2d. Then I can minus 1 on both sides, so negative 2c equals negative 2d. Divide both sides by negative 2, I get c equals d. So therefore, it is 1 to 1 analytically. So now graphically, you want to graph it. And so graphically, you check for a horizontal line test. It passes, and so therefore, it is 1 to 1. Let's look at this next one. So f of c equals f of d, then do I get c equals d? So this one might be a little bit more complicated. So we start with f of c equals f of d. Well, I have stuff in the denominator. I need to get rid of that. So I can multiply both sides by c minus 1, c minus 1, so that cancels out there. And then multiply both sides by d minus 1, d minus 1. So that's going to cancel out there. And so I'm going to get 2c times d minus 1 equals 2d times c minus 1. Well, first, now I can divide both sides by 2, so I don't have to deal with that anymore. So I get c times d minus 1 equals d times c minus 1. And so now I have to try and figure out to get c equals d. So now if I distribute this, if I distribute c to both sides, I'm going to get cd minus c equals cd minus d. Well, if I subtract cd from both sides, those cancel out. So I get negative c equals negative d. Divide both sides by negative. I get c equals d. So it is 1 to 1. Now graphically, if you notice, it passes, it passes, it passes, even here it passes. It passes everywhere. And so yes, this is 1 to 1 because it passes both analytically, that was one way to show, and then graphically. Let's take a look at this one. Now this is where we get an issue here. Now first of all, trying to do this analytically, it's kind of difficult. I mean, if I did c squared minus 2c plus 4 equals, and then d squared minus 2d plus 4. Okay, well I can subtract the 4's on both sides, but now I get c squared minus 2c equals d squared minus 2d. How would I simplify this further algebraically? And the answer is there's no easy solution. Okay, so sometimes trying to figure this out analytically, it does fail us. And so we're going to have to look at this graphically, and graphically, if I were to graph this, it does fail. Now another way that we can try and figure this out analytically is, what if we created a counterexample? So if we tried to create a counterexample, what this statement says is that if I have two y's that equal each other, that means it has to be the same x value. So for a counterexample, what if I find two x values that are different that then gives me the same y value? Because if I showed that two x values are different that give me the same y value, then it's not 1 to 1. So I need to show that negative c doesn't equal d, then f of c equals f of d. So try and show that. Well, what if I picked 0 and positive 2? Well, if I picked 0 and positive 2, they don't equal each other, so 0 doesn't equal 2, so that's so far so good. And if I plug in 0, what is f of 0? Does that equal f of 2? And so if I plug in f of 0, I'm going to get 4. If I plug in f of 2, that gives me 4 minus 4 plus 4, so that's going to give me 4. So therefore, because I showed this statement, it's not 1 to 1. So you can show this. By showing this, it creates that counterexample to where something is not going to be 1 to 1. Now also, if we take points and we were able to graph this, we could also show if something is not 1 to 1. So graphically, if I graph this, I have negative 1, positive 1, 0, 2, and then 2, positive 1. Well, it fails there. So because it fails there, it's not 1 to 1. But also this says where my two y values equal each other, then my two x values have to equal each other. Well, if I look at the point that gives me two y values that are the same, so if I look at negative 1, 1 and 2 positive 1, well, 1 equals 1, but negative 1 does not equal 2. So therefore, it's not 1 to 1. Now in conclusion, what were some of the topics that we discussed in today's lesson? We talked about one-to-one functions. And we talked about inverses. Now what happens with the domain and the range of functions whose inverses are each other's? Well, the domains and the range, if we have functions that are inverses of each other, then they're going to switch. So the domains are going to switch. And then try and give this one a shot. Describe a one-to-one function. Okay, so a way that we can describe a one-to-one function is, you could say, well, it passes a horizontal line test. You can say if, two y values equal each other, so f of c equals f of d, then they're the same x values. Or there's no two of the same y values, there's no two same of the x values. So those are all different ways that you can describe a one-to-one function. So it passes both a vertical and horizontal line test. Well, this does conclude our lesson. If you guys do have any other questions, please leave them in the comments.